Welcome to our online event organized by the Women in Aerospace Europe Rome Local Group. I am the committee secretary of the organization, and today I have the pleasure to introduce you one of our co-group co-leader, Anna Maria Nassisi, that will be the moderator of today's event. Anna Maria is the strategic marketing manager for observation, exploration, and navigation of Thales Alenia Space in Rome, in Italy. And so with this, I have the pleasure to just give her the floor for starting officially today's event.
Thank you very much, Alice, for the introduction, and thank you to all the participants. I would like to introduce some words before leaving the floor to Barbara, by saying to you that last year we celebrate 50 years on the moon landing with Apollo 11 mission, provide us the excitement of the first step on the moon, as Neil Armstrong uttered his famous words, "That's one small step for man, one giant leap for mankind." Now, new era is drawing on us with the NASA Artemis program, which will land the first woman and the next man on the moon by 2024, using innovative technology to explore more of the lunar surface than ever before. It will set up a sustainable structure on the moon and in the lunar orbit to carry out further human exploration of the surface and in various scientific investigation. The upcoming lunar orbital gateway will play a vital role in this process, and by gaining a new experience on and around the moon, will prepare NASA to send the first human, not only men or women, to Mars in the coming year. Thales Alenia Space is mastering all the technology needed to further explore the moon, Mars, and beyond into the universe. We took part to the Lunar Gateway by building the two key modules, and have also a leading role in atmospheric re-entry system with the Space Rider. Now, I'm proud to introduce you Barbara Imhof. She received her education in architecture at Vienna University of Technology, the Bartlett School of London, the SCIARC of Los Angeles, and she graduated from the University of Applied Arts of Vienna in the studio of Wolf Prix. Furthermore, she has a Master of Space Study from International Space University and received her doctorate from Vienna University of Technology. She is an internationally active space architect, design researcher, and educator. She is a co-founder and co-managing director of LIQUIFER in Vienna and Bremen, and interdisciplinary team of experts comprising natural scientists, space engineer, architect, and designer. LIQUIFER's design are about living with limited resources, minimal and transformable spaces, resource-saving system, and the spatial implication of social-psychological factors. Related to this aspect are the running of a system and the principle from nature, which describe the second thematic path in the portfolio of LIQUIFER. Many thanks to Barbara to have accepted our invitation and to satisfy the curiosity of all the people about this new era. Barbara, the floor is yours.
Thank you, Anna Maria, for the introduction. We got to know each other, and we worked with each other for a couple of years in the board of Women in Aerospace Europe. Now I'd like to, I'm really glad that space architecture has become a topic to many people now, and that WIA-E invited me to have a presentation here, and I would present a snapshot of our work, of LIQUIFER's work, and I'll start with a quick introduction into the topic of building in extreme environments. So I'll share my screen now. So I hope you can see the full screen mode now, and not my notes. The talk is titled Out of This World Architecture. So it's something which has been developed, or the profession developed in the last 20 years. And I remember the inaugural meetings with some NASA architects in the late 1990s. So how can I say, I've been in that business for a very long time now. And what you can see here is actually, it is from 1968. It's a view from the movie 2001, A Space Odyssey, which was directed by Stanley Kubrick and conceived by Kubrick and Arthur C. Clarke, who is one of the, I would say, space pioneers, intellectuals, or was. And you see it's rotating station. It's a concept which was developed very early in the, I would say, 1930s or even earlier by first Konstantin Tsiolkovsky and then by Wernher von Braun. It's rotating, and at its ends there's gravity, and then here you have zero gravity in the middle. So it's something probably, just remember the title was 2001. It was presented first in 1968. So that is how people have imagined that, 20 years ago we would be living somewhere in these kind of space stations. It's a very interesting concept because it has artificial gravity and zero gravity, and it combines this. And you can see this quite well here. So this is an interior shot. And so people, the astronauts would come from zero gravity and then would enter into a gravitational zone. So it wouldn't be too hard on their body. So this was the movie 2001 as a short introduction of what people are thinking of when they probably visualize space architecture. In 2001, this is the Destiny module of the International Space Station. So this is what we got in 2001. So not this grand structure, but the International Space Station and this particular module. You also saw before the shot, it was very pristine in the interior. It looked very clean, as does this module when it was delivered to space station. And then this is what it looks like today. Sometimes, not all the time, but you just have to imagine. Sometimes we think, oh, it's all messy and it's crowded, and it's true. But we also have to think that space station is now 25 years old, more or less, and it's and it has, how can I say, it has no wireless connection. So you have all these cables here. Astronauts are constantly rebuilding, doing different elements, and there's hardly any download capability, meaning there's lots of stuff coming up, but hardly, any stuff of going down. So, and all the trash and you can't just burn everything in the Earth's atmosphere, and because a lot of things you'll also need maybe more than one time. So it's like, just imagine you're flat, you're living in a small flat, and you don't have any place to, you're living there, you've been living there for many years, and you just, things accumulate. What's interesting is that in the 70s, so jumping back a little bit in time, there was there were a couple of concepts which are also sort of a little bit eclectic and grand. This is the Stanford Torus. This was actually conceived, well, in Stanford. It was a NASA-sponsored program in 1975, and it also used the concept of, it's a torus, right? So of artificial gravity. It was pretty large for 10,000 to 140,000 residents. So this was really the area when we thought we could establish, I don't know, an alternative world where humans could live. It's also a concept, the torus concept was also proposed by Hermann Potočnik earlier, well, in the end of 19th century, who was a Slovenian engineer. You see here, there's, so it was all supposed to be covered from radiation through lunar regolith. So it was conceived to hang in one of the Lagrange points. So that is the complete zero gravity points between the Earth and the Moon. So on L5, but you know, on between planetary bodies, I would say, or extraterrestrial bodies. So between these gravitational bodies, there are always points where there's zero gravity, and these are called Lagrange points. And so this was meant to have, for example, a diameter of more than nearly 2 kilometers, and an adequate centrifugal force. Another concept, which is also quite famous, was conceived by Gerald O'Neill. He was a physicist also at Stanford. And while he was, he was doing all these calculations, so it's one of the O'Neill colonies concept, but this of course then is a visualization by the artist. It's a cylinder, it's rotating as well. It has a length of 30 kilometers and a diameter of 6.5 kilometers. And it should also be a home for, thousands of people. So, as you see that because it's rotating, that you would have a really nice view because you would have a view towards the sky, but also towards another landscape. So it's quite a different world to ours where we live today. O'Neill also tried to calculate what it would cost to establish this. So he thought that it would cost $100 billion. This, we laugh about it, but probably would estimate that it's at least 1,000 times more, or even, even more. Anyway, for that amount, and this was again in the 70s. So for that amount, for $100 billion, we got this space station. So you just see how the imagination and reality, how different they are, but how also, they inspire each other in a way. So let's look at the space environment or distances a little bit, or destinations. So you see here a map of France and Italy. Why is that like that? Because just imagine, 100 kilometers in z-axis, we reach space, we reach the so-called Kármán line, and where the uplift speed reaches the orbital speed. So basically this is, when you have reached that, so a suborbital flight, when touristic, like Virgin Galactic, so the Galactic, they always speak about suborbital flights. So what does that mean? It actually means you go until 100 kilometers and then you earn your astronaut wings. So this is why this is so important, this line. Then we have low Earth orbit, and up to 2,000 kilometers, and within that is the International Space Station. So the International Space Station is very close, actually. It's super close. It's just, a distance between Rome and Modena. So it's very, how can I say, if you just imagine Rome, Modena, which is maybe 4 hours drive or so, and then, you just go up a little bit instead. and there is the International Space Station. The moon is approximately 400,000 kilometers. These are rough sums, so it's not the exact sum, but just to imagine. So it's 10 times around the world. So if you imagine this and, you know, stretch it out, then you can reach the moon. It's also, there's a funny, you know, calculation. So 24 weeks by train, if you consider you go 100 kilometers per hour on an average. And then Mars is even further. It's, it depends on, you know, because it's all elliptical, right? The orbits between 56 and 150 million kilometers. That would be an equivalent of 1,400 or 3,700 times around the world, or 64 years by train if you would only go 100 kilometers per hour. So that's a long time. So this is about the destinations and distances, which you have to consider when you plan for outer space. But you also have to consider that's a very different environment. So what you see here on the picture, you see Bruce McCandless, you know, floating in orbit, you know, with a little help of some propulsion. But in orbit, we have microgravity. We have 1/6 of gravity on the moon and 1/3 gravity on Mars. So the moon, the lunar gravity feels very close to zero gravity, which is a completely different world where, you know, things are, how can I say, just imagine, you know, you wouldn't sit in front of the computer, but we would all float and hover, you know, in front of a screen. So suddenly you wouldn't need a chair anymore. You wouldn't need a table anymore. So all, you know, you wouldn't need a bed anymore. So all, you have to completely rethink your environment. And you also, you know, the way we move with our body, we hardly use our legs. We might use our legs actually to you know, keep packages between our legs, like stowage packages, and move them, you know, through space station. So it's a sort of reverse. So your arms become more like your legs in the way you move, and then your legs are more, you know, you use them to maybe carry some bags or so. So it's very, outside temperatures, we are very harsh, very extreme, minus 156 to 121 plus. So it depends, of course, on the material. And towards the black universe, you have minus 250 degrees Celsius. So there's a lot of different temperatures. So when you look at that spacesuit, let's look at that. So you see some sun hairs, you see some shadow here. So, you know, here it would be, you know, or on the back side, it would be very cold. On the front side, it's very hot. So that's why astronauts wear these underwear with the water-filled tubes to modulate sort of the temperature of the body. And of course, these are completely airtight. So it's a pressurized environment. It's a small spaceship, because you have a vacuum outside, and that makes the extreme temperature, but also the pressure differences. You have a zero pressure outside here, and you have, you know, maybe 1/3 to 1 bar inside of the spacesuit, depending on your oxygen levels. But, you know, already in low Earth orbit, you have to take care of micrometeoroids. They're, you know, high-speed impacts of grain-size objects. There was, I think it was Luca Parmitano, when he went out for a spacewalk, and then he just, he could see, you know, that from his thumb of the, or finger from his glove, you know, some bubbles coming up. So he knew that there was a leak in his glove, and what did he do? He just, you know, made like this and said, "I'm coming back. Houston, I'm coming back." So he immediately went back to the spaceship. So it's a quite dangerous environment. And you have cosmic rays, because you're not protected by the Earth's atmosphere anymore. So you have a larger radiation, which you have to protect yourself from. So that leads to a couple of challenges for building and living in extreme environments in space. First of all, you have to transport large distances. You have to always think about, what do I really need? What do I need to supply? Can I recycle everything? And I hardly need any supplies. So this is an important issue, the recycling. And Anna Maria mentioned it in the introduction. This is one of our concerns. You probably, when on Mars, you have a delayed communication. So you have to be very autonomous, very independent in this. You have dynamic launch loads, so you have all different things to take care of. So you have to, you have a shortage of space, or meaning you have a minimized space. That could lead to a strategy, to an architectural strategy about deploying and transforming elements. So I don't not only have one chair, but a chair could also be, well, on Mars, let's say, not in zero gravity, a chair could transform into something else, into a bed or so. And one probably would also look, and that's what you can see here on the image, building with in situ materials. So what materials do I have locally, and how can I build structures? We know this from Earth, because when you look at, let's say, Mali and all these mud, clay houses, these are really in situ buildings. And there are these artisan and adobe houses. We also know that from North America. And this is probably a strategy we will also follow when we go to the moon or to Mars. And we have to be very careful with resources. So it's really about recycling, about the utilization, and we have to be independent on the moon or on Mars, and also look at in situ food production. I'd like to start with a project. So with this introduction, you have a little bit a feeling for the requirements and the parameters we need to look at when we design for space. So I'd like to get into, show you a project. It's the Lunar Gateway. Anna Maria mentioned it. We are currently working for Thales Alenia in Turin, because they are building the International Habitat module, and we are doing the interior configuration design. And they are not only building the hull, the envelope, but also the interior, like the full thing. Here is one configuration, and what I'm showing here is actually our previous study where we worked with Airbus and Thales Alenia on the project. It's a small configuration, so it's here. This is the International Habitat module. This is the stack for the lunar lander. You see here the legs and some other modules. This is the Orion here. This is the propulsion module, and these are other logistics modules. The final configuration, to be honest, is not set yet. So there's always, change for, there's always room for changes. I'd also like to mention, because that's sometimes a little bit mixed, it's getting mixed up, that Artemis is not Gateway. So Artemis is the American program, and Gateway is the international program where Europe has a main part, plays a main part. And but the interesting thing is with Artemis is that, these women, they're all candidates to land on the moon, and that's what also Anna Maria mentioned in her introduction. That first we will see in the next years, we will see the first woman walk on the moon, and they will also probably visit Gateway and the International Habitat module. This is another configuration for Gateway. It's larger. You also see here that there are different ESA components. It's mainly the space station partners, NASA, JAXA, Canadian Space Agency, maybe Roscosmos, also not sure yet. And so it's the same, basically big consortium which built the International Space Station. So while it's, I'll show you a little animation from that, actually from the design, which will explain a little bit more the actual design we did. So while space station is in a low Earth orbit, Gateway is much further away, is 1,000 times further away, so it's a more dangerous environment. There are many unknown factors, and before going to Mars, we really need to learn how it is to be, to go around the moon, to be in this like more extreme environment than low Earth orbit with more extreme radiation, and to train for this. So here you see this is the International Habitat Module. This is the current version we're designing. I can't show you anything of this, but so this is an older version, but it shows you what the crew functions are. So there are functions like exercise, an exercise facility. There are also crew quarters and galley and science. So there's everything, like everything a crew needs to inhabit a space like this is packed into one module. This is 5 meter length and 4 meter in diameter, 3 meter 50 in diameter, and now we had to shrink it even a little bit more. So you see that it even becomes, it's really a very challenging design task. So what does a module like this comprise of? What are the main elements? Very important is stowage, right? I mean, we always need, somewhere to stow supplies and food, etc. We'll also have a little kitchen, a galley with a food warmer, and of course, trash compactor. We'll have a table, very importantly, for coming together, for social gathering, for having the crew of 4 come together for dinner. Exercise facility, we have crew quarters, and here you see this is deployable. So we really try to, have one status of the crew quarter during the day, and during the night, the private spaces become more important, and the crew has a larger space to sleep in. There's the toilet. It's also deployable because only when you need it, you have a larger space, and otherwise it's really smaller. This is the glove box. So this is the science equipment, basically there, right next to it, and the control station. So we assume that the station will be controlled basically by tablets. These are system boxes and the life support system, and together they take up quite a lot of space. And currently they are developed by JAXA, by the Japanese Space Agency. And this view really gives you a glimpse into, the small space. The good thing about zero gravity is that space appears to be much larger because we are floating and we can access all different, sides. You saw that with the toilet. Toilet was on the top, although there's no real top. And important is really that the crew can come together and, and exchange stories and maybe talk about the day and have a dinner together. So this was a design we are currently working on. It's a real, it's going to be flight hardware in a couple of years. Before, I'm going backwards a little bit in the timeline. We were working on other projects which led to our engagement in IHAB. This is the project SHE, the Self-Deployable Habitat for Extreme Environments. And here, this is really about the deployability of spaces. So SHE is meant to be a test bed. You see that in the simulation. It's a test bed for simulations on Earth. This is in the Mars analog area in Rio Tinto in the south of Spain, in Andalusia. And SHE is deployable because what you see here, this is the deployed state. It's 50 cubic meters. It's similar to IHAB in that sense. It's meant for a crew of 2, so you have 2 private crew quarters. You have a workspace here. You have a sort of hygiene facility, sort of bathroom, limited bathroom here. You have another more workshop area here, and you have the galley here, communal space. What you'll see, what we built later was were the suit ports. You see that later. But the thing is that everything here needs to be foldable. So here are the beds. There's the workspace. Everything like this just folds into that middle part. And then it looks like this. This is in the you know, being deployed. This is during the making. Here you see a little bit a glimpse of the inside. You see more later. And so that's why you can transport it on land to different analog sites to use it as a test facility. On the other hand, you can dock different SHEs together. She is a nice word, right? It's not he, but it's she. And you can also put it, you know, back to back into a large launcher. This was the Energia, but it could be any other large launcher. It's 6 meters in diameter here. So from this, I'll only show the deployment mechanism. So you get a little bit of, because of time, I shorten it a little bit. So here you get a little bit of a glimpse of how it's being deployed. These petals. So the middle is sort of the size of a ship container, standard container. Here you also see the suit port. This is the galley. So this is where people come together and sit. This is the public area, sort of public area, which is very important. And here the private areas. Because of the space and the way it's designed, I mean, I lived in the SHE, and I have to say, you know, you hardly hear anything from the other side, and it's all without doors. It's just through the shape and the geometry. Here's the work zone. We also established acoustic panels here. I hope the video one runs well. And this is the middle zone with the small galley, the refrigerator. So you see that most of the elements, they're always the same, right? We have a kitchen, we have a bedroom, we have a workspace, and this applies to all environments where humans live. And this is here you see that's the little workshop, the wet compartment, we called it, and the hygiene compartment. It's also foldable, but you see that it's sort of transformable, deployable, foldable, just to be able to compress it in this small central area when being stowed and transported. And then these are the suit ports. They're quite important because it's a way of not having cross-contamination. So when you go to Mars, then you don't want to contaminate with your own microbiota, you know, Mars, because then the life you'll find is only, you know, yours and not the Martian life. These are just quick, you know, photos when it was ready. These are Waltraud Honeder, co-managing director, René Václavicek, also co-managing director. Here you see them again. You see the crew quarters and the galley. And then we had the opportunity to take it into Rio Tinto. And then again, you see how different it looks like. You know, you remember these two pictures of the Destiny module, before and after, sort of. So this is when it comes into life. So the wet compartment turned into a local Martian mission control station. This is the Capcom. Here are the medical doctors testing the Simonaut, the simulation astronaut, before they went into the simulation. These are operations of getting into the suit port, docking from the habitat and exploring the surface. We also had an astrobiology laboratory. These are people, Spanish people from INTA, from the Spanish Research Institute. And so what we didn't have with SHE is we had a living area, we had sort of working area, but we didn't have a food area, because, you know, humans need food. So we, after SHE, or, you know, while we were doing SHE, we already started Eden ISS. It's a project for a greenhouse. And what you see here is another simulate, a very good analog for space. It's Antarctica. So we built a greenhouse facility under the lead of the German Aerospace Center in Bremen, and put it to Antarctica. It's still there. It's in its 4th year, I think, already. And it's there to test a very specific way of growing food. It's called aeroponics. You see, it looks like a jungle. We have tomatoes here, we have salad, we have Swiss chard, we have cucumbers, all kinds of different vegetables. And we were quite successful because what you will also see here when Paul Zabel, empties or harvests the vegetables, then you see these boxes, and in these boxes are the roots. They're hanging without soil, and they just get a spray of water and nutrition every 10 minutes, very much tuned to what this particular plant needs. And therefore, it's a very limited material we need to grow very successfully these vegetable garden. And what you see here, the shelf area is 10 square meters altogether. And within 9 months, we produced over 270 kilograms of fruits or vegetables, which is really a lot. And this is without the biomass here, the leaves, which you see Paul is putting away. So this is the life cycle of a plant. You see how fast it grows. It's of course, it's a time lapse of 3 weeks. So every 3 weeks, there was another harvest, basically. So now we have the habitat, some workplace, we have the greenhouse. And, when we look at our next goal, the moon, the surface of the moon, then we also have this very harsh vacuum environment. We have to, micrometeoroids and radiation, and we have to protect ourselves from that. So we need some kind of radiation and micrometeoroid shelter. And we can do this with using in situ materials. So we can use the soil, the material from the lunar surface. And we were part of a project, it was called Regolite, and it was about solar sintering, interlocking elements. And to be honest, I just see that some slides are missing. So let me try to explain without these slides. So solar sintering is a method where you concentrate a solar array and you have it it falls onto a sort of table. It's like 3D printing table, let's say. It's an additive layer manufacturing process where some sand is put on, a layer of sand, and you sort of glue these layers of sand together until they reach a solidity like this one. So you only need the sun and the sand, these two components, and they are for free, in abundance, available on the moon. And in this project, we made 3 printing campaigns. So we made one in a protected environment with artificial light, and we sintered different kind of geometries. We made another campaign with a big printer, which could be also put on a little rover. So it would be a moving solar sinter printer. And we made one other printing campaign in vacuum, because it's actually a similar environment than on the moon. And we did this specifically to advance the technology readiness level of that particular technology, the solar sintering technology. As architects, what did we do in this? We looked at the different scenarios. So you saw the scenarios here. This is one scenario. You see how these elements here by a robotic means are being put up and form these kind of dome-shaped houses or envelopes. They could protect rovers from radiation and micrometeoroids. So machinery, you'll need a lot of machinery for infrastructure, even for robotic infrastructure. And also to create thicker protection for human habitats, basically. And what you see is that they have all these kind of shapes, these sort of dome shapes. And then when you look at the sintered material, you can also see that probably it's not, you know, if you put tensile stress on it, it probably will fall apart. So what the material is good for, it's good for compression, like, you know, non-reinforced concrete. So on a, you know, structural engineering level, we thought, okay, if maybe our shape should be more towards a catenary line. You see, you know, catenary line like this cannot take any compression forces, but if you sort of invert the change the structure 180 degrees, you get suddenly a geometry which cannot take tension forces but compression forces. So since this is what this kind of solar sintering technology, non-reinforced, can take, we decided to find geometries. That's why everything's sort of dome shape, which look a little bit like this. And then I told you about these printing processes. So the printer is, okay, I say the way we worked with engineers who built the printers from Space Application Services in Belgium, but we also worked with the German Aerospace Center. They're material scientists, so they looked at the granular material of these of that lunar dust, basically, or the lunar soil simulant. Yeah. And while doing these different printing campaigns, we looked at what was the outcome. You know, when we look at this, we also see that you cannot do any sharp angles, right? Because here it breaks up. So we needed to design to come up with a geometry which has a more, you know, which has no sharp angles, which is which can be packed and stacked. You see, these are all stacked. They're interlocking, basically, like these. Yeah. So when they come together, they look like this then. So they are rhombic dodecahedrons. This is a space filler geometry, which is also used for packaging. There's no, there's zero gap in between. And then we tried to find sizes for elements so that they could be, you know, a little bit larger. And then finally form different kinds of dome geometries. So we wouldn't need too much scaffolding, you know, some substructure to put it on top, because it was self-sustaining. And then we looked at, you know, different geometries with connection points. So here's one connection point, here's a second one, then something, a shape like this, or 3 connection points. And that's what you also see on the final image, basically. And this is how we then thought the whole configuration would look like. So we would have inflatable structures here in the middle. We had, you know, through the connecting points, we had transitioning modules. We had a cupola here, and then the protection was the in situ solar sintered envelope. Like this in the middle here. So I'd like to recap a little bit. I also have backup slides if there are any questions. But when we look now at the elements we need for a Moon or Mars base, we need some stationary elements. These would be these habitational or inhabited domes. And in there we would have a greenhouse, we would have maybe a modular basis or some inflatable structures. We would have mobile elements like rovers, smaller rovers you see here, but here it's hardly visible. There's a pressurized rover, so it's an excursion vehicle like this one. This was also a project we did with Thales Alenia Space, actually, in Turin for ESA. And we would need EVA tools. So there's one project Moonwalk. You saw briefly when I explained the SHE module, where we also did simulations underwater, and we designed these tools for astronauts, especially for the lunar surface. Then, before we start creating a base like this, we have to do simulator studies. So you see here a couple of simulator studies we did for the European Space Agency in the last, I would say, 20 years. And another topic, and this concludes the overview in that sense, another topic is the in situ resource utilization, which addresses the project Regolite, but also a Mars project we did, Lava Hive, which is here, won the second prize in the NASA 3D printed habitat competition. But we're also looking at nature and biology and trying to analyze or translate biological systems into architecture, integrated into architecture. And that comes very handy when we look at bioreactors, which can recover resources and integrate them into possibly life support systems. And all these projects, so we have already been working on, and they are an instrumental part for a lunar or Martian base. And at the same time, the topics we are concerned with, like the limited space, the shelter basically, or the waste management, water, energy, air, these are all topics which are very important for today's cities or for the development of our environment here on Earth. And so in parallel to all these space projects, we also are working on a project which is called The City as a Spaceship, where we look at self-sufficiency, sustainability, resource recovery and recycling, and see how we can also apply the concept of a spaceship for a city. And yeah, I think this was the last slide. With this, I'd like to thank the whole team. I'm now open for questions. Thank you for your attention.
Thank you, Barbara, for the fantastic presentation. It was a very dreaming presentation where the science fiction novels seems our reality today. And it's important to highlight that what I introduced at the beginning for you, that the importance of interdisciplinarity team, because you have well addressed the importance to know from different angle of view. This is very, very important. And also about the very difficult environment that we know very well by manufacturing our satellite. But it's a very difficult for the human that have to live outside. Very nice, very nice. Also, there's architecture in a small space in order to be efficient, to have all what we need. I think that we can stimulate for a question that can be submitted directly to you, Barbara. Any question about the participant? I didn't know the chat. Okay, Sabrina. Sabrina, we start with Sabrina Melchion. that is our member in Bremen. We start with her question.
Yeah,
Sabrina?
hi. Thanks for the presentation. Yes. It was very, very interesting for me. My question is that I heard that for the habitat, there is also on studying kind of windows, but at the same time, there are you have to protect your habitat from radiation. And so I'm asking to myself all the time, why windows and not maybe screens or something to project some other nice images? I don't know, that is just not black or red or gray.
No, I think that's a good question. It's always a trade-off between these things. So let me show you here this image again. What you see here in this, that is actually a so-called virtual window. It's on one hand, you can get different light atmospheres, which changes the space. So light is a very good, I would say, architectural material in that sense, that can create different spatial atmospheres and change the space completely. And it could also, of course, project from the outside an image to the inside in a safe way. But I think that probably that we are humans, and I think we realize that especially in COVID times, that we are very much dependent on some physical perceptions in that way. So I think that probably I can imagine that we will have a window, but maybe this is more sort of I don't know if you see it here. Was it here, or it's in the last page? Maybe it's a very specific space. You cannot access it frequently or for a long time, but you just have it to get a view, or maybe to have a small telescope, or some kind of, so that you can sort of get a feeling for sort of personal, creating a personal relationship with the place you are in and with the environment you're in.
That is the same that we have on ISS with the cupola that is built by us.
It is the cupola, actually.
Yes. Greta Sondi that has submitted a question, but Greta, if you want, you can ask directly to Barbara.
Okay, thank you very much. Yes, I'm a biology student, and I'm very interested in kind of biomaterials for space, and I would like to know if there, besides the like the Terra printing with the Terra material, are there any other kinds of biomaterials that are used in space architecture, or or are there some in the maybe just start with that question.
Yes, actually, that's a good question. I think there are studies that have been conducted by the German Aerospace Center, Bremen, in Berlin, about using mycelium also for radiation protection, partly, and also finding out if they could survive in a Martian environment. So they made different kind of studies, and there's a whole sort of architecture, microtexture, using mycelium-grown structures, especially also for the interior. There's a study going on, and experiments at Ames Research Center.
Okay.
So that would be. And then, of course, we'll have to see what we can, microbes can also transfer, maybe create bacteria cellulose, which could be also an interesting material. But it's, for now, I would say it's in the beginning, that kind of research, to see what we can use in space, what kind of biomaterials we can, or grown materials, self-grown materials we can use in space.
Okay. So
but we can also, maybe there's another way, you know, we can, let's look at the greenhouse. And remember when you saw Paul Zabel, you know, harvesting, there were a lot of leaves. And you could, so the leaves are made of cellulose, and you could create a 3D printing material from cellulose. It's a different approach, but you can, you know, then use that kind of cellulose to 3D print new stuff.
Okay, sounds very interesting. Thank you very much.
Yeah.
Barbara, we have another question coming from Patrizia Galeffi. Patrizia, the floor is yours.
Okay.
Patrizia?
Eccomi. Hi.
Okay.
Hi.
Listen.
Anna Maria, we can't see you anymore. Your camera has vanished.
Okay.
Ah, the camera, so probably. Okay.
I have activated my camera.
I don't know. Okay, doesn't matter the camera.
Until Barbara is sharing the screen, so that will be the one that everyone will see.
Okay. Anyway, the question is a very small question. I work in ENEA, that is a nuclear agency of Italy, and my department is biotechnology and agro-industry. In our department, we have done some patenting about horticulture and mini greenhouse and vertical farms. Do you know something about that? About these works? I mean, we were testing some specific greenhouse for cultivar, for growing crops and tomatoes, potatoes, some edible vegetables, as you show also, and different way to grow these vegetables instead of course, gravity and without water and with very little consuming about these fundamental resources, of course. And no, my question was if you had the contact with this group, and if you could be interested.
Which group are you referring to? The Italian group?
No, the group in ENEA that works on these activities.
No, I don't.
You don't know these people?
No.
Okay. The name of the group leader of these things is Eugenio Benvenuto.
We worked with CNR on this, so with the Italian company, a couple of Italian partners on this greenhouse.
Okay.
So there was TASI on the life support system side. There's CNR. I don't know what the national research, the Italian National Research Agency, I think it's called. I don't know what the Italian name is. So
okay, no, because it could be interesting to have some collaborations. I know also that they have done some experiment in the base in Antarctica also about this kind of greenhouse, special greenhouse. So
this was a very large, with a lot of partners. I would have to look them up. There's also Aerospace, I think they were called, with a minor role. So, but there's a whole website on it, and there you can also see all the partners involved. So I'm not sure. I don't think that the group you're mentioning we have been interfacing with, but probably they know of this project, or they have delivered something to somebody else of that project.
I don't know exactly which kind of funding they have done, they have used, but I know that was a very good work also about this kind of issues, and interesting program. Very interesting.
Yeah. No, it's very important also, because it will be also important for you know, looking, you mentioned vertical farming, so creating you know, within our urban structures, creating larger greenhouses And I think the Japanese are very much in the front line of the development of this technology, because they want to be independent. They are an island state in that way, and they are very good in producing their fruits and vegetables.
Yes,
and
of course. Yes, yes.
Yeah. But also for other remote areas, of course, in Alaska or Siberia or wherever.
Yes. Thank you for your seminar. It was really interesting. Thank you.
Thank you for being there and for the question.
Barbara, we have the last question coming from Francesco Ventre. Francesco, do you want to submit directly the question to Barbara? Very short, because yes, I read your long question.
No. So basically the question is really short. First of all, thank you for the seminar. It was very interesting. And secondly, I would like to ask you if there is any planned real mission to test this technology. And also, I asked in chat, I mean, if I can reach you privately, because I have an ongoing project that will be tested during an annual mission. So I would like to discuss something with you, and I don't know if I have to refer to the website, or do you want me to give like you know, any email address? Anyway, thank you.
Okay, so yes, our website is you saw that in the final slide, is this one, and you know, there's also an email you can contact us at. That was quickly answered. And the other question was what?
Yeah, it was regarding if there is any real mission, not analog, already planned to test this kind of technology.
Which kind of technology? There were a couple of technologies I presented.
Yeah, I mean, for example, the lunar one, so the sintering. The
sintering, yeah. Well, we did test it 3 times on Earth. With under different conditions in vacuum, and also in an ambient, so in a laboratory setup with a completely automated printer or manufacturing table, and also, and then a 3rd time with a larger structure where the concentrator was a Fresnel lens. But we haven't tested it. So we have tested it in vacuum, but we haven't tested it in space. There currently there's a lunar lander missions foreseen, so that will be an opportunity to test this technology in space. But before that, actually, we will need to advance the readiness a little bit, so that we can be sure that in the vacuum chamber we can produce really good sintered elements.
Thank you so much.
Okay, Barbara, I think that we have over the time. And your presentation was very, very stimulating, and I think that a lot of other people will come back on our registration that will be available on our YouTube channel as Women in Aerospace. And if you can eliminate the presentation, we can have all the people around the table, virtual table.
Yes, sorry.
Otherwise, we don't see anybody. Oh, wonderful. I don't know why I don't see myself. I don't know. And I would like to thank all for the participation, and in particular to you for the fantastic presentation, and to offer us this dream of the new era. where we are the new colonists for the Moon and follow on for Mars.
Thank you, Anna Maria, for inviting me. Thanks.
Okay. I discovered which is the problem.
Now we can see you.
Yes, it was the picture of my amplifier. Thanks to all, and we wait for you for the next seminar that we are planning with other fantastic guests. Thanks again, Barbara, for your availability, and see you soon.
See you soon.
I take the opportunity also for greetings, for to be at health for all, and for a fantastic new year to cancel 2020.
Yes, Merry Christmas and Happy New Year to all of you.
Thank you very much.